All right, so let's talk about rational exponents in 6.4. So we're continuing the lesson from 6.3. We're going to be talking about just basically thinking about these things in a slightly different fashion. So radical expressions and rational exponents. First off, you can write a radical expression in an equivalent form using fractional exponents instead of the radical sign. So in general, the nth root of x can be written as x to the 1 over n. All right, so basically you're just putting a 1 over the index, putting that as an exponent, and these mean the same thing, all right? For any positive integer n. Like the radical form, the exponent form indicates the principal root. So, for instance, the square root of 36 can be rewritten as 36 to the 1/2 exponent. The cubed root of 64 is 64 to the 1/3, and fourth root of 16 is the same as 16 to the 1/4. All right, so let's simplify expressions with radical exponents. So what is the simplified form of each expression? Well, if we have 216 to the 1/3, keep in mind this is the same thing as saying the cubed root of 216, which means we can just do a factor tree here. 216 divided by 2 is 108. 108 divided by 2 is 54. 54 divided by 2, or 54 is 9 and 6. 9 is 3 and 3. 6 is 2 and 3. All right, so we've got, this is cubed root, so groups of 3. So we got 3 2s. We've also got 3 3s. With nothing left over, so this is actually 2 times 2 times 2 times 3 times 3 times 3 gives you 216. Or one group of 2s, one group of 3s, 2 times 3 is 6. Okay. For b, we have 7 to the 1/2 times 7 to the 1/2. Well, again, this is the same thing as the square root of 7 times the square root of 7. We know that the square root of 7 times the square root of 7 is just 7. And we get our answer there. And then for the last one, 5 to the 1/4 times 125 to the 1/4. So 5 to the 1/4 is the fourth root of 5 multiplied by the fourth root of 125. Which, if we break down real quick to make our lives a little bit easier, we can do a factor tree of 125. 125 is 5 and 25, and 25 is 5 and 5. So this is really just the fourth root of 5 times 5 times 5 times 5. Okay, this whole thing is just equal to this. And of course we have 4 5s here, so we can just call this 5. Where we got the 4 5s, you're probably asking that. 1 5, 2 5, 3 5, 4 5. That's where we're getting our 4 5s from. All right, checkpoint. Again, feel free to pause and work these problems. I'll put the answers on the board. First one's 8. Second one's 11. Last one is 6. All right, rational exponents. If the nth root of x is equal to 1 over x, it follows from the laws of exponents that all real numbers, the nth root of x to the m, would be x to the m to the 1 over n exponent, which is the same as x to the 1 over n to the m. And we know that whenever we are multiplying exponents, which is, again, just x to the n to the m, okay? I'm sorry, the nth root of x to the m. This leads to the definition of rational exponent, okay? So a rational exponent says that if the nth root of a is a real number and m is an integer, and m over n is in lowest terms, then a to the 1 over n is equal to the nth root of a, and a to the m over n is equal to the nth root of m, or nth root of a to the m, which is also equal to the nth root of a, all to the m. So this all means the same thing. The big idea, though, that I want you to get is this piece right here. we can change something that looks like the right side into the left side by making sure that the index is on the bottom and our exponent is on the top. So let's convert between exponential and radical forms. If I have x to the 3/7 and y to the negative 3.5, how would I write these in radical form? Well, it's quite simple. The first thing you note is that the first one is already set up properly. So we end up with x to the 3rd with the root 7 out front. Another way you could write the same thing is you could say that the 7th root of x all to the 3rd. These mean the same thing. So either way, you're perfectly fine. Now the second one here, y to the negative 3.5, how we would write that is we first have to change it into a fraction. So what is negative 3.5 as a fraction? You can check this in your calculator if you want, if you don't want to do the math. But negative 3.5 is just negative 7 over 2. So this is saying y to the negative 7 over 2. And then from here, we can just do the exact same thing. Y to the negative 7 over 2 is equal to the square root of y to the negative 7. All right. Now, y to the negative 7 is the same thing. Well, whenever you have a negative exponent, that puts that into the denominator. So this would be 1 over y to the 7th. Square root of 1 is still 1. So we end up with 1 on the top and the square root of y to the 7th on the bottom, which we can then simplify to 1 over, we can pull out 3, so y cubed, square root of y on the bottom. And then we can actually just rationalize the denominator by multiplying the top and the bottom by square root of y over square root of y. And this gives us square root of y over y to the 4th. All right, the whole reason we have to do this is because we just can't have a square root in the denominator. We know this already, so we have to rationalize the denominator. The simplified form, fully simplified form, would be square root of y over y to the 4th. All right, what about square root of a to the 5th and the 5th root of b cubed in exponential form? This is much simpler than what we just did. So keep in mind that the index, whenever you can't see it, is a 2. So this would be a to the 5/2 for the first one. And the second one is going to be b to the 3/5. Remembering that the index of your root goes into the denominator, your exponent goes into the numerator. All right, checkpoint. It is your turn. I will put the answers on the board. For the first one, you should get the 8th root of w cubed over w, and the 5th root of w. Oh, put those in the wrong spot. And then for the second one, we should have x to the 3/4 and y to the 4/5. All right. Moving forward, we got a word problem here using rational exponents. Kepler's third law of orbital motion shows how you can approximate the period p in Earth years it takes a planet to complete one orbit of the sun. Use the function p is equal to d to the 3/2, where d is the distance from the planet to the sun in astronomical units. How many Earth years does it take Mars to orbit the sun? All right, so this isn't too bad. We're given the equation using a fractional exponent. And so p is equal to d to the 3/2. We can plug in we can plug in 1.52 AU into the distance. So 1.52 can go in to D, and we've got 3 over 2 to the 3 over 2. And using our calculator, we can approximate our answer to 1.87 Earth years. Oops. 1.87 Earth years. All right. So, with that said, here's your checkpoint. Find the approximate length in Earth years of each planet's year. So Venusian year if Venus is 0.72 AU from the Sun, and a Jovian year if Jupiter is 5.46 AU from the Sun. Well, go ahead and pause it, and if you want to work it, you should get 0.61 Earth years and 12.76 Earth years. All right, let's talk properties of rational exponents. You should have learned this previously, but just as a reminder, if you're multiplying bases, you add the exponents, okay? If you have an exponent to an exponent, you multiply the exponents. If you have two factors to a single exponent, that exponent actually distributes through those factors so that each factor gets that exponent. If you have a negative exponent, that term goes into the denominator. If you are dividing bases, you subtract the exponents. And if you have if you have something divided by something else to one exponent, then each of those actually gets the same exponent, just as the same as whenever you're multiplying two factors. So, combining radical expressions. A couple of lessons ago, we discussed that you can only combine radical expressions with the same index. All right. However, you can work around this limitation if you convert them to expressions with rational exponents. All right. So, what is the 4th root of x cubed over the 8th root of x squared? Well, to figure this out, the first thing you want to do is actually convert both of these to fractional exponents. So we end up with x to the 3 over 4 over x to the 2 over 8. Well, the good news is that we actually just talked about how to deal with this. Looking here, we have two things. We're dividing two things. We've got, oops, I'm looking at the wrong thing. We're dividing two things with different exponents, which means we can just subtract those exponents easily enough. So here, it's actually the same as saying x to the 3/4 minus 2/8. So as long as the bases are the same, we can actually subtract these normally. 3/4 minus 2/8, if we get a common denominator here, actually gives us x to the 6/8 minus 2/8, which gives us x to the 4/8, which is equal to x to the 1/2. So if we were to convert this back into just the square root form, we end up with square root of x. All right. Checkpoint, your turn. Use these properties of rational exponents to then simplify these expressions down into their simplest form. All right. So what is each product or quotient in simplest form? The first one is the 4th root of 27. And the second one is the 6th root of x to the 5th. All right. Simplifying numbers with rational exponents. So what is each number in its simplest form? We've got 16 to the negative 2.5. Well, first off, if you were to plug this into your calculator, you would get a decimal. And that's not what we're looking for. You actually get a rather large decimal here, which is not something that we're actually looking for in the end. What we want to do is we want to convert this over into something that we can actually use that's really useful. So if we have 16 to some exponent, first off, this is a negative exponent. So it's going to be 1 over 16 to the 2.5. 1 over 16 to the 2.5, remember that we can convert decimals into fractions. So this would be 1 over 16 to the 5 halves. 5 divided by 2 is 2.5, yes. Which then can be rewritten as 1 over the square root of 16 to the 5th. Square root of 16 to the 5th. Okay, so that being said, we end up with this really, it looks kind of ugly right now, but that's okay. So we can pull out 16s as pairs, okay? So there's 5 pairs of 16, so I can pull out 2 of those pairs. That's 16 squared out front, which leaves us with, by the way, we don't need this 2 here, the square root of 16 on the inside. Well, the good news is we know exactly what the square root of 16 is. This is actually 1 over 4 times 16 squared. And 4 times 16 squared is 1024. All right, let's look at B. And in B, I'm going to do this slightly differently. I'm going to show you a slightly different method. So we end up with negative 32 to the 4/5. We are already in fractional form, so I'm not going to have to change anything. But what I am going to do is I'm going to change negative 32 into something a little easier for us to deal with. I know that 32 happens to be 2 to the 5th, all right? So I can rewrite this as negative 2 to the 5th, all to the 4/5, okay? Well, the reason why I went this way is because I see that I've got 5 to the 4/5, right? So I've got an exponent to an exponent, and if that happens, we multiply the exponents together. So this is the same thing as saying negative 2 to the 5 times 4/5. Well, the 5 and the over 5 in the denominator go away, and we end up with negative 2 to the 4th. It actually simplifies really easily into just negative 2 to the 4th. Negative 2 to the 4th is positive 16. So this is our other method we could definitely use here. It's maybe not as user-friendly because you have to actually know things like what is 32 in terms of 2, right? It's 2 to the 5th. So if that's not the way you want to go about it, you can easily just do your math this way. All right. So here's your checkpoint. Answers are 1 over 8, 8, and the difficult one, 1 over 2,187. All right, last example of the day. To write an expression with rational exponents in simplest form, write every exponent as a positive number. So in the end, we don't want any negative exponents. So what is each expression in its simplest form? All right, let's go through this. This is a very complicated one here. So we've got negative 8x times the square root of x to the, or xy. Everything is to the 2/3. Well, first off, let's break this apart, okay? So this is the same thing as saying negative 8 to the 2/3 times x to the 2/3 times the square root, which is really xy to the 1/2, all to the 2/3. Okay? So I'm rewriting this a little bit. This can be then rewritten as negative 8 to the 2/3. Negative 8 to the 2/3 is, I'm going to use that trick that I just talked about a while ago. I'm going to change 8 into 2 to the 3rd power. So I've got negative 2 to the 3rd power multiplied, or to the exponent of 2/3 times x to the 2/3 times xy, all to the 1/2 times 2/3. It's going to be 2/6, which is 1/3. All right, I can continue doing this. Negative 2 to the 3rd to the 2/3 gives us negative 2 squared. X to the 2/3 times x to the 1/3 times y to the 1/3. And we're continuing to simplify here. We get 4, because negative 2 squared is 4. X to the 2/3 times x to the 1/3 is just x. And then we end up with y to the 1/3. And we can leave it like this, or we could rewrite this as 4x times the cubed root of y. Both of these mean the same. For b, doing the same thing, we end up with 16 to the negative 3/4, y to the negative 8 to the negative 3/4. This can be rewritten. 16 is 2 to the 4th. So we have 2 to the 4th multiplied by negative 3/4 multiplied by y to the, don't need this, 8 times 3/4 is 6, y to the 6th. All right, so this equals 2 to the 4th times, 4 times negative 3 to the 4th is just 2 to the negative 3. Y to the 6th. And 2 to the negative 3 is 1/2 cubed times y to the 6th. Lastly, we can say that 2 to the 3rd is 8, so y to the 6 over 8. Y to the 6 over 8 is our most simplified form. All right, that stuff is complicated, I totally get it. So if you want to rewatch that part, please do. Take into account that I'm using a whole lot of these rational exponent properties. So please reference back to this as you're going through it. It's going to help you immensely, I promise you. All right, checkpoint. Your answers are going to go up on the board. And my computer just died. Nope, there it is. Cool. So the answers that you should get here, for A, you should get 1/2x to the 5th. And for b, you should have 27x times the 8th root of x to the 4th y cubed. I guess that's it for this lesson.